that is allowing us to predict which kind of polarity we are waiting, for example, from P waves radiated by a double couple. Why double couple? Representation theory. Where? Far from it. Far field, far source. So we're going to study essentially the radiation pattern of a double couple. That's very recap. Is that fine? I don't know if for you it's not a recap.
No, it's not a recap, but I'm going to recap it.
Okay, so you're going to work in the future for the past. Good. Okay, starting point. This is what we collected until now. We can use that one. We can use the expression of a G. And let's remember that if you perform the algebra, the spatial derivative is giving us some radiation pattern, plus with the change of variables, what's happening there is that the spatial derivative is giving us a time derivative in the source time function. That's nice. Now let's give a look to this dot first. Now remember, we squeezed all the information in one point. So what we have just missed is the information about the initial part of the rupture, the propagation of the rupture, the end of the rupture. We will call it, or in one of the last slides for today, or on Monday, rupture time. So please accommodate one place more for dinner, because we cannot avoid it. It's very important. But for today, it's not there, because everything is in a point. What is left in a point? Well, it's the time necessary for that point to slip. And so we can imagine a simple sketch here. For example, instantaneous source. It takes no time to slip. Well, the derivative will be the delta. Is it realistic? No. No, it's not. Is it useful? Well, maybe. If you're going to use your study period so long compared to this time, you can take it as a step. And you can consider it an instantaneous source. Good. But in a more realistic fashion, it's going to take some time to slip. With maybe some wiggles here, but okay, let's take it as a ramp function. Good. Then the time derivative is a box. It's a box that is lasting that amount of time. That time is called rise time. Okay. What's next? We have a P wave field, we have an S wave field. That's a retarded time for P, retarded time for S. Spherical waves, good. They are decaying with distance. Question, especially for you two. Now let's imagine that our body is not infinite. Yeah, it's not. The Earth is not. It's bounded with a free surface. Maybe it's layered. So we have surface waves there. Can you imagine that the Green's function, for such a medium is not made just by P and S? It's made with all the waves that can propagate in that medium. These are the slides that I was skipping in the last lecture. Please do remember that surface waves do not decay as 1 over r, but they decay as... Thank you. Okay, that's important. So in a realistic signal, we don't have just a P and S, we have all the reflections, all the refractions, plus surface waves that can dominate the signal somewhere. Good. Okay, then we are left with this normalization denominator here, that is containing the cube power of velocity. So we should wait that this is smaller, so this is larger. Yes. And then we have radiation patterns. Okay, now we can use this one guessing. Okay, given a source, given a double couple somewhere, if we know where the source is, and we collect the information around the world, can we predict what are the polarities? Yes, we can. And that's the game that we're going to play now. Now, a different representation that should relax you because it's coming from a science session textbook. Here it is, the picture that we need. Because now the reference system will be centered into the source. And this is very natural because actually we will use a sort of a spherical reference system with a distance, that is the radius from source, and two angles that will be needed to specify the position of the receiver compared to the source, colatitude and longitude. Now please use your imagination because along R direction there will be a P wave, and this means compression or dilatation. Then on a plane that is perpendicular to R, so in theta and phi direction, there will be S, as you do remember. R is this. Oh, it's not written here. Should be this. And it's a versor, a unitary vector pointing along the distance. So let's imagine that we have a receiver here. That's R. That actually is okay. And you have to imagine a unitary vector here pointing along this direction. So that's a R, like in a spherical system. Okay. While theta and phi will contain the information about S. Question: should we distinguish between SV and SH? What do you think? I think the same. So I fully agree with you, but in the medium that we treated during the last lecture, there is no need because it was infinite, homogeneous, so there is no reference surface. But we have the free surface of the Earth, of course. So sooner or later, SV and SH will enter into the game and radio waves. PSV, SH, radio. Okay. But in these sketches here, there is no need. What we know is that the S wave field will act in a plane perpendicular to R, so in theta and phi direction. Okay? Now, the most important picture is this one. Because actually, you have a game along phi, but if you take, for example, phi equals 0, so in this plane here, okay, you will have 4 lobes that depend on theta. And you see here a big plus, big minus, big minus, big plus. So we have 4 quadrants and 2 null axes, because along those axes there is no radiation. Okay? This is the picture that we are going to use to predict first arrival polarities, P waves. What about S? Well, it's a little bit more complicated because it's representing a plane perpendicular to P. So if you stay along R, you have just P. But you see here, we have 2 components. Because of course, here, you have to imagine a plane, but of course we'll have 2 coordinates here. So the net result of the radiation for S waves that is larger, please do remember, because alpha is larger than beta, okay, it will be like this one. So it will be 0 in 2 points that are exactly where the maxima and minima of the P waves. So 0, 0, 0 on this side and 0 on that side. And on a sphere, you see, we will have different shear displacement. It's shearing. Please do remember that S waves do not change volume, right? While P waves, they do change volume. And that's their property. Remember, the curl of something and the divergence of something. How to measure the divergence of a wave field? Sorry, I'm giving to you the answer. Just give it. How to measure the change of volume that is induced by a wave field? Thank you. So if you take the divergence of a wave field, you get the measure of the change of volume. Because this is exactly what we called and, pardon, my day, and we call it long time ago theta. And it's not zero for P waves, but for S waves it's beautifully zero. Okay. Can we use this piece of information? Yes. And now this is what we're going to do. Another sketch coming from the last session textbook, but it's nice because now you have to imagine to take the radiation pattern, to look it from one side. This is the arrangement of the body forces, or you can imagine also a slip on the fault, like in the specific case that we considered. Do you remember? The slip was here, and that was the normal. And it could be replaced by a double couple. Okay, the radiation pattern induced by that slip or by the double couple is this one for P and S. It's complementary for lobes. Because now we're looking at a section along phi equals 0. So essentially it's a sine of 2 theta and cosine of 2 theta. Simple, right? Okay. Now, before going on with the slides, what are you waiting? Now, let's imagine to take the source, to embed it into the Earth. Let's imagine to have a free surface. Yes, we have a free surface, okay. And let's imagine to spread a set of instruments in the world. What are you waiting for? I give you a telephone and the numbers, the phone numbers of all of the stations. But don't look at me, I don't have the stations. What should you look for? If you embed this picture inside the Earth, you have to imagine that these arrows here, okay, they're going to decay with distance. But sooner or later, you have to imagine rays departing from a source, wave fields. And we are going to carry an information. Oh, well, we are carrying a lot of information. M.0. Let's forget. We are carrying the information about the medium. Maybe we have to forget. We want to forget, but we cannot. But we will solve it in a very simple fashion. The amplitude will diminish with distance. But wait a second, because here the information will be a push. So if you have an instrument there and the ray is arriving pushing, the first arrival should be up. So it will be a compression, right? That actually will correspond to a tension for the source, because it's pulling the source, pushing the receiver, okay? So the t-axis will be maximum there for the source. Please do remember, from your eyes, I see that you're, maybe I was hiding it here. Yes, it's hidden here, but it's coming from the, please do remember this. So you see, t-axis for the source will be a push for the receiver. Okay. And this is what we're going to do, to use this piece of information. Now, according to the position of the receiver around the source, for example, if you imagine to have something here, it will be a pull. So it will be under, less than 0, the first arrival, then whatever. That will be the piece of information that we have to imagine to carry down from the receivers to a sort of a strange imaginary sphere that is surrounding the source. It's called the focal sphere. And let's imagine that a push will be marked by a black dot, a pull will be marked by a white dot, and you carry this information on the focal sphere. Okay? Now what? It's not easy to use a 3D object. Let's make a projection, a stereographic projection. So a sphere will become a plane. And we will see it from the top. Okay, that's the focal mechanism. End of the story. We can go. No, we can't, but in principle, yes. Now, a vision letting you to remember, letting us to remember that a radiation pattern is a 3D object. It's the antenna, okay? It is radiating into the space. It's not 2D, it's 3D, with its slopes for P, S, and all the other waves that will come later. Let's remember that usually, at a given distance, the radiation will be larger for S. Now you know why. On average, the two radiation patterns are complementary in terms of direction of maximum radiation. And if you want, you can play with a nice... What I was putting here? Oh, I was putting this because it's coming from an old... Now 3 slides that are coming from an old some romantic textbooks. But let me tell you that if you... I put the link somewhere, I guess. That you can download for free this visualizer of Mathematica applets, and for example you can play very easily with the radiation patterns, changing the strike, but changing the strike is nothing but changing in this direction, changing the dip, and changing the slip. You see, it's always the same. It's going to be rotated according to the focal mechanism of the style of faulting that we have at the source. And P and S, they are different, please do remember. P has 2 nodal planes, you see, 1 and 2, while S has 2 nodal axes. You can divide it also by SV and the SH, but not for today, because we don't have a free surface. So you can play with that, it's just a rotation. The 3 angles, 2 are defining the fault. Which fault? We have a double couple. And the slip on that fault, which slip? Okay, it's the moment tensor. If you change the geometry, you're just rotating this into the space. Okay? Okay, what's next? Okay, this picture, I left it here because it's a sort of a summary up to now. It's an old-fashioned summary. Fault plane, the slip, the coordinates, the reference system that we can use to describe this, and radiation pattern, and a sphere around it. And you see that this imaginary sphere is divided in quadrants, with compression and dilatation. So you have to imagine 2 are black and 2 are white. And this will be projected in the receivers around the world and around the sphere. These 2 pictures are coming from Aki and Richards, and they are nothing else than a different summary of what we discussed until now. Is it okay? So that's for P and that's for S. And this is the slip on our simple, well, not that simple, but our specific case that we discussed for the representation figure, coming from Aki and Richards. Good. Now it's time to go to represent them with the tool that is in jargon called beach ball. And it's a nice tool, because all the messy things that we have been discussing until now, representation theorem, thousands of expressions, the Green's function with hundreds of expressions, can be summarized in the far field, far source, far field condition with very simple graphical objects. Now, what is the main point here? That thanks to a stereographic projection, the sphere that we have seen will become a sort of a 2D picture, in which planes, y planes, the fold, they will become lines. Vectors, which vectors? The slip vector, we have just one now, it's the average, remember, will become a point. And rays departing from a source, they will become points. I'm not a geologist, so I cannot explain in full the next, or I'm not researching geography, you will see the next slide. But the main idea here is this: how to make a sphere, better half of a sphere, a plane. Well, like that. Let's imagine that that's the portion of the Earth where we have a fold, we have a sphere around it, the upper part. Let's imagine to see it from the top. That's the convention that is adopted in seismology. And let's imagine to see it from the top. Well, if you see it from the side, you see it's like that. But if you see it from the top, this line here will become this. Nice. That's the strike of a fold, and you can imagine that this is the dip. How to measure it? Well, it depends on the stereographic projection that you can use, that you want to use. The most adopted in seismology is this. It's called the equal area. But the idea is, again, it's coming from a thing called geometry. I think the Greeks were the first to study how to project a 3D object into a 2D. For example, this is the solution. So our focal sphere will become plotted into a stereographic net like that, where you can measure angles. That's it. It's just a convention. Let's see an example, for example. And let's start from a fold plane. Now you see, that's the sphere. It's cut. Let's throw what is over the surface. And what we need to describe it is vector knee, right? Yeah. Yes, but for today, no knees. Just strike and dip. But it's the same. Two angles define a plane. Okay? That's Z, strike and dip. You change one of them, you will change a knee. So the knee that was in the representation theorem, if you remember, there is a slide coupling that knee with U and, the knee with strike and dip. Okay? Good. That's the strike of a fold, and you can measure it. It's 100, in this example, 109. Okay, you count, that's 90, 109. Then you have to imagine to put 109 at the pole there, and you can measure the dip. It's 55, okay, you count. 10, 2, 3, 4, 5, 5. Now you rotate it back again, and that's your fold. Is that enough? So, strike and dip, knee. Now it's a line on this net. Is that enough for an earthquake? No, because then, and that's the most tricky part, we need to discuss what is the motion of the hanging wall respect to the foot wall. For example, it could be, that's the rake, or the direction of the slip vector. Okay? Could be transcurrent, it will be left, right, thrust, normal, or whatever. So we need to put a third angle there. It's called the rake. Now, in the direct approach, if you know the rake, it's easy. Also, if we need to discuss a convention here. For example, let's imagine to plot an arrow there at a given angle, for example, 90, okay? Now you can imagine the third vector that is getting out from that part, that, okay? Now let's imagine this. Now this is giving a direction of the hanging wall respect to the footwall. We call it rake. We call it also U. It's the sleeve vector. That's the direction of the sleeve vector. You should say, but there is also an amplitude. Well, not for today. How to measure it? Well, now we have to adopt some conventions. For example, we could use this angle. Yes, it's 270. It's a normal fold, right? But we have a problem, because we don't see the upper part. So it's better to use minus 90. It's the same, okay? Good. And there you go. Now this point here is telling to you which earthquake is happening. So for example, if you put a point exactly in the middle here, or here, and you put a dot there, that will be the final information. It's minus 90. Problem. I will let you think before trying to answer. How to plot a thrust fold? Because now the vector is getting out. Oh God. And we don't have the upper part of a sphere. It's only convention. Relax, my friends. We could use the same, because now the vector is there, but we cut the sphere and it's out. Well, okay, to point this, let's point minus it, and it is here in the same part. But what will be the difference? So again, a point here. I'm anticipating. Again, you can put a point here. Okay? But it's telling to you, okay, but it was going the other side. Can you imagine what's going to change there? I'm challenging you. The sign. Well, okay. For the sign, well, okay. Instead of being minus 90, let's take it, instead like this, let's take minus this, okay? That's easy. What's going to change in the radiation? Because in one case, it's giving like that. In the other case, it's pushing.
So compression to...
So, right. So you're doing, I hope, using intuition, that one is pushing up, the other is pulling out, okay? So the color will be different in the middle. One will be black, the other will be white. That's the difference. That's the only convention to remember. I've just anticipated what we're going to discuss next. So that's a fold. And I was adding some pictures here just to relax you, because these are coming from a Seismology section. They are telling the same, okay? So you can measure the dip there and the strike there. Okay, easy. We are on your textbook. A similar exercise, but coming from Seismology section, but I guess you have. What else? That's important. If you're by the way, if you're going to perform a study in focal mechanisms, maybe you can relax, because now everything is done by computers, by codes. So you don't have to. But 20 years ago, you should use a stereographic projection by hand, okay, rotating it. But now it's performed by codes. But it is important to remember that when you perform focal mechanism inversion, and when you use a code, you have to think about the assumptions that you're assuming. For example, are you going to switch the flag pure double couple, then situation will change because you are forcing your inversion to assume that one of the eigenvectors is 0. And in the mathematical flow, it will act something. And that means that, okay, the pictures that you are going to see in some slides will have a specific shape. By the way, let's imagine that we have this plane here. What about its pole? What is a pole? The direction of the normal. Now, if you go back to one of these slides here, for example, you have to imagine that we have a normal to that plane. It's called the pole. Now, in the sphere, it will describe exactly a point at 90 degrees from this. So you have to measure 90 here, 1, 2, 3, 90. That's the pole. It's the projection of a normal of a fault. And through that pole, they can pass all the planes perpendicular to the initial one. They are all perpendicular. It's just a property of the stereographic projection. That will be important. Oops. What's next? That's the example of the ray. So if you want to plot something that is where the eigenwall is getting down by 20, you have to put a dot here. So actually, a slip on a fault will be described by one line, one meridian if you want, plus one dot. All the dots here in different position, they can describe different slips at different angles. Remember that you have to think about the sign of that point because you have also to express something that is thrusting, but you cannot see it because you're taking just the lower hemisphere. So you have to remember that this could be plus or minus in some way. And the inner part will be black or white. Okay, what's next? This is the final step. Now we need also to imagine how to plot the rays that are the directions perpendicular to the wavefronts that are leaving the source in all the possible directions, right? For example, this ray here is leaving the source with a given azimuth, okay, and a given, this will be called takeoff angle. Now, this ray here that is touching the sphere here will become a point, exactly this one. So rays, they will become points. Question, how many points should we plot in principle? All of them, right? Because from that point, they will go everywhere. So you can imagine that here, we should have an infinite set of dots. Which ones will take in consideration? All of them? No. Which ones? Do you have some favorites at some angles? That's the crucial question. Which ones? Actually, we should look at this problem from the reverse point. Because we have, I don't, but maybe you will have receivers. So now we have to imagine that we have a word around our source here, okay?
Draw the line from the source.
Okay, well, you know what? That's the difference between geophysics, applied geophysics, and seismology. Because in applied geophysics, you decide where to put the source. Hammer, okay, I'm going to hammer here, and I deploy my geophones there. Good. But for seismology, we cannot decide where to put the earthquakes. It's vice versa. So we have networks. Let's imagine to have a network, beautiful network. But it will have a finite number of instruments located maybe on mainland. Good. Actually, we will use just the information received by the receivers. So just a few rays can be used, the ones that are leaving the focal sphere and reaching the instruments. Question, let's imagine this is the point. Will be the ray path like that? Well, the question is for all of you, but yes, no.
No, not exactly, but maybe pushing. We don't like that.
Is the trajectory a straight line? Well, maybe.
Maybe.
In a homogeneous medium, it will be a straight line. So a ray of light is going. But if we have here additional layers, Snell's law. And we go back to the wave physics section when we describe the rays inside the Earth. And maybe you know that, for example, if the Earth is characterized by an increased velocity in depth, it's not, but okay, we will have a tilting. So we will have trajectories that will be curved according to the structure of the Earth. Do we know the structure of the Earth? Well, we can do our better, and maybe to use at a global scale a spherical reference model, PREM, you should remember. All this part is in the wave physics course, but I hope you do remember. Okay. So when you are solving for a focal mechanism problem, there are two important steps. The first, you should know the position of the source. Do we know? To some extent. But of course, we will have uncertainties. That's one of the sources of the errors. If you know the distance and the position and the distance to the receivers, and if you know the structure of the Earth, then you can trace back the rays that are here to the sphere. Actually, you're going this direction. And you can put the points there. And you can do this. With the black or white information, according if here it is positive, or here negative, then here you will put a black dot and here a white dot. So that's the trick. But there are some assumptions. Far source, far field, P waves. The position of the source, of a point source, so it's a point. The structure of the Earth, and then you can try to get the focal mechanism. Remember that there are many sources of errors, or of uncertainties. Position of the source, the distance from the source, it should be far, otherwise it's not a point. And maybe someone here at the station was reversing polarities. Two cables. Okay? And the plus is not a plus, it's a minus. It was happening a long time ago. I think it's happening again. I'm not an instrumental seismologist. But okay. So this source of errors can reflect in the final focal mechanism solution. But the idea is this one. So to use the information collected around the world to ask, okay, is it up or down? Up, 0, down, okay. That piece of information is traced back, and then every ray, if you know the structure of the Earth, can be mapped here in a point with a given azimuth and to a given takeoff angle. Because then Snell's law will decide the path of a ray. And I hope you do remember troubled times. And that was T, was delta, and the T over the delta was called ray parameter. This part has been discussed in the wave physics course, absolutely. But it's here. You definitely remember.
Yes, I remember now.
Okay. And so that's the piece of information that is used to trace back the rays, to assume an Earth. And that's the idea. So focal sphere, rays are living wherever, but we can collect just some of them. It depends on the arrangement of the stations. And we ask to our friends, now you can use your phone book, your phone, and you ask, okay, plus, minus, 0, and so on. And this is an example, for example, of tables. These are a little bit old, but still valid at the global scale, where you can use the information about the structure of the Earth to trace the rays back. So you know the distance, and according to the distance to the station, that's the takeoff angle that you can use to plot black or white dots. And what are you waiting for after all this procedure? Well, actually, you're supposed to see on this projection, stratigraphic projection, 4 quadrants separated by black and white colors. And according to their distribution, okay, now you can say, oh, we have a fault with a given strike, with a given dip, with a given rake. That's the focal mechanism. Is that true? No. And let me tell you why. But this is the convention. This is one of the last slides. It's a little bit different than the one that you have printed, I guess. Do you have the printed one? Is it exactly the same?
Yes, I think.
You're a mathematician, right?
Yeah.
So you should be very sensitive to differences. Ah, because you are using the, can I say it?
Yes.
There should be a small difference. Come on, you're a mathematician. I'm a physicist. I can say, oh, they are the same. You cannot. Look at the links. There are 2 there, right?
Ah, okay. I was looking at this.
I'm a physicist, I can forget. No, okay. One link disappeared. Actually, I should ask Stefan because it was at GFZ. No, the picture is one thing. I was asking. No, I'm joking. I was asking about the slide because I changed it yesterday. The piece of information that was very nice. Actually, that's where it's here. It was produced and shared by the European Geophysical Union on GFZ's website, probably moved, but I was not able to find it.
Oh, sorry, this is now on the module.
Now it's on your screen.
But it's not on the module.
Not yet,
Okay.
because I want to test it first.
Okay.
Because I was leaving on the caption what was reported in the caption of the GFZ link, and it's quite important because it's the convention that I was mentioning to you. So when if maybe you work at focal mechanism procedure, you will have to know this convention. And if you're reading focal mechanism, you should know this convention here. That is the one exactly that I was telling to you. Now let's imagine that we did our work. We collected the information. We painted with white or black dots. With some tricks, we have been able to separate with 2 meridians, black and whites. This is the picture that we can get. Now, first message to you. We will never be able to distinguish between the fault plane and the auxiliary plane. Why? Because the moment tensor is symmetric. And you and me cannot be distinguished. Do you remember?
I didn't get the what's plane and what's plane. I didn't get the names. I'm sorry.
Actually,
It's written later.
Oh.
But, where is it? Long time ago, in a remote galaxy, we had been discussing this.
I remember this one, but
If you remember it, then you will know this.
Okay.
Now, that was the piece where the point where we decided, okay, let's consider just a pure shear dislocation. Then just mu is there, and what is left is this. Now you can change ni and you will get exactly the same. So if you take ni and you can take ni and you will get the same. So black and white will be distributed exactly in the same way. The symmetry of a moment tensor has the consequence that we cannot distinguish between the real fault plane and the other one that is called the auxiliary plane. We cannot. Just using radiation and polarities. So that terminology is reflected here. Which one of the two planes? Who knows? Well, if you want to describe an earthquake, then you know which one is it. But if you're making the inversion, you cannot distinguish. By the way, let's consider this one, for example. Okay? That's the strike. Easy. The dip is always measured to the right of the fault by convention. Okay? So the dip can be measured here. Now, what about the rake? That's a little bit more tricky. Because now you have to take the pole of this plane here. Easy. It has to pass on the auxiliary plane because u and ni are separate, they can be exchanged. Then you can draw the other plane and you can take the pole of that plane, and that will be defining the rake. Now, that's the rake. How to measure it? This is the convention that I was telling to you, and this is what I reported. Everything depends if in the middle we have black or white. Remember, if it is tension for the source, okay, it will be a plus for the receiver, okay? Plus means black. And if it is black, it's thrust. And so this angle here is 180 minus this angle. It's pointing there, out. If in the middle there is a white, that is a normal, because it's pulling, it's a pressure for the source, then it's minus lambda. By the way, the fault could be this one. The strike will be there, the rake will be there, and the slip will be measured here. You cannot distinguish them. Can you? Can we? Actually, yes. Because maybe, well, can you imagine, these are two faults. One has a strike along this direction, okay? The other one has a strike in the other direction. Let's knock on the door of some geologist. Maybe he or she will tell you, okay, look, here the faults are along these directions, so it has to be this. That's one possibility. Ask to geologists. Second, look at the distribution of aftershocks. Third, use some information about an extended source. But we cannot do it now.
How are you going to get the information from aftershocks?
Because you will see that the... okay, let's imagine this is the fault plane. Okay? Once you crack, the other cracks will be around here. If this is the fault plane, the cracks will be around here. So distribution of aftershock should reflect, in principle, the surface of weakness. So accordingly, they are distributed here or there. but it's an additional information. What I want to say is that if you don't plug in some additional information, you cannot distinguish. It's due to the beautiful symmetry of the moment tensor. Okay? Let's go towards the end of this part of the story, and this is a picture coming from your textbook. And now you should be able to see how different patterns should give to you immediately a sort of an idea of a style of faulting. For example, this is a strike slip. This is a thrust and this is a normal. And you should tell me, please tell me, why?
Why?
Homework. But it's a very nice one. Now I will go through this beautiful movie produced by USGS and IRIS, cutting part of the story, but please look at it because it's, to me, it's very well done. No formulas here. Most of the first part should be in your pocket, so that's why you will
When
not.
an earthquake occurs, seismologists create graphics of focal mechanisms, informally referred to as beach holes, to show the faulting motions that produce the earthquake.
Now,
The focal
I will
mechanisms
jump,
are based on the
okay?
direction of the first arriving P wave.
You
Let's
should
investigate the patterns of P wave arrivals that result from different faulting mechanisms by first considering a strike-slip earthquake. When an earthquake occurs, seismic waves
Now,
radiate away from the epicenter.
That's the simplest. And it's the only one for which you will see the 4 quadrants on the focal mechanism. You know why? Because the focal mechanism, by definition, is the projection of the lower hemisphere and seen from the top. That's the only possibility to see 4 quadrants, like for example in California, because they have a lot of strike-slip events. And you should know this because elastic rebound theory.
Parallel green lines in the northwest and southeast quadrants have been compressed during the earthquake, and the northeast and southwest quadrants were stretched. Let's look at the P waves moving away from the epicenter. We will insert slinkies to demonstrate and exaggerate the compression
This is just for
and
P.
dilatation features. Northwest and southeast of the epicenter, the rock is compressed, and the first arriving P waves at those stations are pushes away from
So
the epicenter.
plus black.
Northeast and southwest of the epicenter, the rock is stretched, and the first P waves are pulls toward the epicenter. The
Okay.
dilatational and compressional arrivals are often shown as plus and minus signs, respectively. With observations,
So now you see, that's already the focal mechanism. That's it. Because now we're looking from the top, the fault. We can't because the fault is there.
these stations, we see 2 quadrants of compressional arrivals and 2 quadrants of dilatational arrivals.
So
separated by
tension
perpendicular
and pressure
parallel
axis,
planes.
okay?
To simplify the illustration, compressional quadrants can be shaded, and dilatational quadrants are left unshaded, producing
Good?
Yeah.
Easy. No formulas.
a P wave first motion pattern that looks like a beach ball. Notice that this pattern of dilatations and compressions can be produced either by right lateral strike-slip faulting on a north-south fault plane, or left lateral strike-slip faulting on
That's the symmetry of the moment tensor. From that plot, you cannot say which is it. It's the same. So you and me, or let's now this is
east-west fault
there,
plane.
or me
Therefore,
and you.
you must use geological knowledge of the region to decide which
And that's
fault
the double
plane is
coupler.
the fault plane. For example, if an earthquake with
Okay,
an epicenter
let me
on the
jump to
center-
another part of it because it's, I hope it's still resisting. That's the interior of the Earth. That's for you, okay? I want to look at the normal. That's transparent. That's your homework, remember. I want to go. Here. Okay. Uh-oh.
dilatations that result from an earthquake on a normal fault
Normal
on the east
fault.
side of Steens Mountains in the Basin and Range Province. The block on the east side of this fault has dropped down with respect to the block on the west.
So, strike, dip, and rake. Okay?
Viewed in cross-section,
Okay. Now, if you take the focal sphere from the side, it will reveal 4 quadrants. Because 4 quadrants for P waves are everywhere. But the point is that at the end of the stage, we will look at it from the top. And we will lose that symmetry, apparently.
compressional first arriving P waves will radiate to the east and west from the hypocenter at shallow and intermediate downward angles.
That's black and white, 4.
Dilatational first arriving P waves leave the hypocenter at a steep downward angle. The
4.
resulting focal mechanism has perpendicular nodal planes that cut the lower hemisphere of the focal sphere in an
That's the point. So for normal and thrust, you cannot see the 4 quadrants with this projection. You can see it from a side. Okay? So that's the strike, that's the dip. How to decide the rake? Well, it's white inside. If it is white, then it is pulling for the receiver, if you remember. If it is pulling, it's P for the source, that means normal. So from the top, you will see a pull. Which one is the fault? Well, here you know, because you see the fault, and it's this one. But it could be also this one. Same strike, but with a different dip. Okay? So your homework is to see again, to watch again this very nice tiny movie. Okay? It's very well done. It's illuminating, especially this picture here. You have a link here. Then there is another beautiful piece of information, and it is a PDF document made by a geophysicist, actually a geologist. And it's very nice because it's recapping many things here, with some additional information about faults from a geological point of view. But you will see the same plots here, the same plots. And there is something nice in his description, because maybe I'm an old man. And one thing that you can remember, when you see this white and black, if you want to remember the style of mechanism, you have always to imagine that the white is going to be black. So the dark force is getting you, Star Wars, okay? And you see that one. So if you want to remember, white is going to the black, to remember directions. Okay, that's a trick. It's not my cup of tea, it's coming here. It's coming from here. Okay. So when you see black and white, you should be able to remember what is going where. But you know, there are some prequels and continuation of Star Wars. By either way. So give a read to it. There are some practical exercises, but the information is the same. You see black and white, focal mechanism, and so on. So this is additional material that I'm leaving to you. And now let's try to conclude this part, and that's the summary. Strike slip, normal, thrust, oblique. So where this situation is a sort of a mixture. This is a first graphical summary. So you could say, please don't say. So we had to discuss a representation theorem with a very painful lecture, yes. Green's function with a very painful lecture, yes. Far source, far field, radiation pattern of P waves, the plotting conventions, everything is squeezed into this information, and that's another summary here. And it's, well, the final slide for this part is this one that is very important because it's collecting everything and it's coming from a science section textbook. What we will do in the next 20 minutes will be a sort of a very quick look to the consequences of beach balls and how they can be used to draw information. And then, in the last minutes, I will ask you, okay, that's beautiful, but what are we missing? Okay, by the way, this is the situation, okay, as a sort of a dynamical vision. Dynamical, why? Because we have forces, okay? So pressure, and remember, pressure for the source. This means a pull for the receiver, white. Tension, it's a tension for the source, it will be a push for the receiver, black. Now, what is this? Well, we don't know. Because one plane will be the fault with its normal, and the other one will be the slip. Remember, come to the dark side, okay, so it could be like that, or like that. We are going to give exactly the same radiation pattern. And if you give a look to this system here from the side, this will be, for example, the strike will get out from the plane. You will measure the dip, and the rake will be the direction of slip. In this case, it's thrust. Now, if you do remember the convention to take the lower hemisphere and to look from the top, this is what we're going to get. And P, T, and P, remember, they're always 90, 90, 90, 90. And the fault plane and auxiliary plane will divide them. So 45, 45, 45. It's perfectly symmetric. And vice versa for the normal. So please do remember, black, thrust, white, normal. And black will contain tension. Why? Because, well, it was up for the receiver, tension for the source. Okay? Tension for the source. And, okay, that's the sketch telling you, okay, that's the null plane, P, T. So all the vision that we had when we squeeze all the information in one point can be mapped here. Can we use that? Yes, we can use that, and a lot of people is using that. So please do remember focal mechanism and stress axis. Stress for the slip on the fault. Remember one thing, please, that the information that we're getting here is telling us something about the state of stress at the moment of the earthquake. Right? So we see this, we say, oh, it's a thrust, so we are in a compressional regime. It's a normal, oh, extensional regime. It's a strike slip, oh, we are in a place like California or around the ridges. That's important, because with these tools, starting from, let's say, 1965 and on, people was using seismology for tectonics. You can say, well, that's trivial. No, it was not trivial at all, because tectonics and geology were totally separated by seismology at the time. And why the 60s? Well, because to perform this analysis here, we need signals. So, actually on Monday, before going to, on Monday we will conclude this part with some final questions that I will ask you today. And then we will study briefly the history of seismometry. You could say, why? I'm not an instrumental seismologist at all. But actually, we have to know that only after the end of the Second World War, unfortunately, there was a large spread of instruments. For technological reasons and for political reasons, but only after the 50s. Seismic stations were around the world, and we need stations to do this. And only after the computer processing of signals, this analysis can be performed. So 68, that's why I was leaving here on the Moodle website just a paper that can be used for night reading because it's really emotional. The date is 1968. It has been published by 3 very famous seismologists that at the time they were working at Villamonte Observatory. What is funny, the order of authors, I always love that, was just by lot, okay? And the title is Seismology and the New Global Tectonic, because there was no inference at the time about tectonics. And if you, well, maybe you know better than me, these cartoons here, 1968, it was a revolution, but there is a very nice plot here, transfer of faults. I think no formula in this paper. You can see lithosphere, stenosphere. Also the distribution of earthquakes in depth was giving this piece of information. But what I want to see, to show to you is, okay, something like that. Okay? And something like that. So focal mechanisms are used to infer the state of stress in some regions. Please do remember one thing from the first lecture, that in many cases, state of stress is not creating new faults, but maybe sleep is occurring on a pre-existing fault because it's more convenient from an energetic point of view. So the TMP axis maybe are just a proxy, but maybe the fault has been created with different TMP at the time, okay? So it's not a direct piece of information. Let's imagine that you're creating a fault under an extensional regime. You create a normal with a given angle. Now let's imagine that something is changing. Now you're going to compress it. Well, instead of breaking a new fault, it's better to make a thrust on the existing fault. Okay? So you will see, the distinction between compressive and extensional, but let's not trust blindly to the orientation of the axis in terms of angles. Okay? By the way, this is the picture that I wanted to show to you, and this will be about the final slides that I'm going to show you. But, okay, to a set of warnings now. First, moment tensor is giving us much more information than the piece of it that we use today. Because, for example, we can imagine to live in a world where we have very peaceful explosions. Let's imagine what is the radiation pattern. Well, if everything is plus, all the receivers will get a plus, right? So the focal sphere will be totally black. If it is an implosion, well, it will be vice versa. If it is, and please remember the eigenvalues, okay? Minus is here. Or maybe we can see beautiful double couples, right? So the trace is 0, and one of them is 0. This is a strike slip. These are deep slips, perfect. This is a thrust, okay? But there are some strange moment tensors that are mathematically allowed, but they should not reflect the part of pure shear dislocation. What I'm trying to say is that if you're going to perform seismic tomography or focal mechanism inversion in volcanic areas, you may look for a percentage of some explosion. So maybe it's the case that you don't fix that the total trace is 0, or that one of them is 0. Otherwise, you will fix the focal mechanism to be perfectly like that. You see the lines are perfectly joined, creating a quadrant. But maybe there is a percentage of it that is not a double couple. So please do remember this. Moment tensor is allowing you to create something more, how to say, less annoying, yeah, but not less sophisticated, but because the tensor is the same. Okay, but remember that you can get some percentage of different focal mechanisms than pure double couples. The pure double couples are here. You see? Is here. Second message, which is a general message according to what you're going to do in the following of your studies. What we did today was about P waves. We could use also S waves, but it's a little bit more complicated. Why? Because we don't have nodal planes, we have nodal points. But we can do it in principle with direction of shear. And actually what we can do in principle is also to use surface waves. Now what are surface waves? Rayleigh waves and Love waves. And Rayleigh waves are P and SV. Love waves are pure SH. So you can use the piece of information that we had been looking at before, and you can build also the radiation patterns for Rayleigh and Love. Now, wait a second. If you want, the expressions are in the hidden slides of my last minus, not today, but the previous lecture. But I don't want to be cruel. And they are, where is the Green's function? You see they are hidden. That's the Green's function. Okay. That's the expression for the radiation pattern for Rayleigh and Love. Of course, Rayleigh will be a mixture. Love will be just pure SH. So it's simpler. But what you have to remember is that you can build them, you can compute them, and the difference is that, okay, for lobes mainly, but as usual, they are complementary. When one is maximum, the other one is complementary, on average. Message to take home, you can do the same also for Rayleigh waves, okay? And that's the end about the theory for today. And now, a very quick overview of what you can do. What are the normal folds? So now you can take a global catalog and look for white inside. And if you give a look to them, well, they are what you're waiting for. Normal fold. So extensional regime. So for example, oceanic ridges. It's full of them. There are many others in alpine belts or Apenninic belts. But on a global scale, you can look for them. Look how beautifully they are depicting the ridges, because there you have expansion. Or rifts, rift zones. Now what about the reverse folds? Well, you are waiting for compression. And the most important ones, maybe they are along subduction zones. What about the strike slip? Well, some crustal deformation places like in California, they should be here, right? And around the oceanic ridges for transform folds. Remember that in this case, the vertical stress is intermediate. Then you can use them also to do some other study like continental zones. Like you can ask Karim, he has been performing a lot of studies on the African rift. So in rift zones where you have separation, you will look for normal. You see the white inside? And another nice picture that can be taken is about subduction zones following slabs. So maybe, definitely at the beginning, you're waiting for compression. But later maybe gravity or some other dynamic forces are trying to pull the slab. So maybe along the slab penetration, you're going to get some normal folds here. So you are waiting for white inside, and again maybe compression where the slab is feeling some resistance deeper. So the general message is, okay, looking at the focal mechanisms, you can receive hints about the tectonic regime. These are the good news. Now, yes. let's say 9 minutes. Good. It was a relaxing lecture compared to the Green's function representation theory, right? And you can read also the beautiful paper in the published in 1968. And you can also relax with this, because there is a picture. Well, rupture is supposed to be something like that. Now, that picture is coming from an old paper published by Norm Haskell. Haskell was pretty much everywhere in the 60s as a seismologist. He created, actually, I'm still using codes that are based on what is called Thomson-Haskell method to solve the equation of motion in layered media. But he published a lot of papers also on dynamics, seismological dynamics applied to seismology, but he published that beautiful paper there. And, okay, there is a keyword in the title. And that paper was so important that actually what we're going to study to conclude this part, but we will conclude it on Monday, is an extended fault. And that model is called Haskell model. Now, and the picture, the cartoon down in the bottom, is just showing, not with an animation, but with the snapshots, how the rupture on the Sumatra event in 2004, you see it was 26. That's wrong, by the way. Okay, the rupture is taking, wow, 300 seconds. And we've seen it also in Toku. It's taking minutes, the rupture. But today we have used a point source in the far field, but a point source, so far source. And we left something out. Yeah. Is it important? Maybe yes, because the slip in one point on the fault maybe can take seconds rise time. But that one can take minutes. And we're neglecting it. Well, we can't neglect it, of course, as you can imagine. And we will give a look to the simplest extended source model that we can imagine. He imagined. And why is it simple? And we can work it algebraically. Well, because it's saying, okay, let's imagine that we have a fault with a given length and a given width. Let's imagine that the rupture is starting from one side. It's starting here. So the first element is breaking. So it has a given strike, dip, and rake, whatever. The rake is not specified. Could be thrust, could be normal, could be strikes, whatever. This is going to break, then the next one is going to break, the next one, until the end. It will take a time. And the time will be the length divided what we will call rupture velocity. And this rupture will be called unilateral rupture, because it's going from one side to the other side. Okay? Why is it simple? Because it's a rectangle. Rupture is starting from one side, is ending at the other side. Everything is constant. Rupture velocity, amount of slip, the rake, whatever. Everything is simple except that the rupture is starting and propagating. This will give us the second kinematic time, and this will be called rupture time. That is not the rise time. That's the time for one point to slip. So we will have a rise time here, a rise time here, a rise, and so on. The consequence of this model, that is called Haskell model, but it's just the simplest model for an extended source, will be very important for two things, at least for two considerations. First, that with a moving rupture, we will have what we call directivity. Because you can imagine that if you are a poor receiver and the rupture is coming to you, or if you are a lucky receiver on the other side, well, that's not said, and the rupture is going away from you, the signal that you will record there and here will be totally different. Like when you hear a sound source and the source is moving. When the train is coming and the head is blowing, you feel the Doppler effect. It's an effect related to the fact that the source is radiating in time and moving. Okay? It is called directivity. And it is important also to study seismic source, but also it's very important for seismic hazard, because the seismic input will be totally different. The second and maybe most important consequence of the Haskell model will be that the spectrum, what we are going to call the spectrum, so the radiation in the frequency domain of a seismic source, will have a specific feature. The end of the story will be called the omega square model. And let me just anticipate it, and this is what we're going to do on Monday. If you want to plot the amplitude radiated on average by a seismic fault in frequency according to different moments, we'll have a sort of a shape that is like, nah, I don't like it. Now, let's take the logarithm. And the logarithm of this, -1, -2. The two slopes will be -1, -2. And this two corner frequency will depend by 1/TR, and this will depend on 1/tau. What is my message is that the source spectrum is not flat. You know what? Let's imagine that the source spectrum is flat. For all the frequencies, it's flat. The only quantity that will be important could be M0. So you're getting a larger event, larger event, larger event. Okay, you're just scaling your signal by multiplying by a scalar. Okay? Well, that's not the case, because the seismic source is not radiating like that. It has a omega square, 1/omega square feature. So it's a filter, if you want. Now, the only way to get this picture, simple picture of a source spectrum, is to go through the Haskell model. What does it mean? That we have to move from the hypothesis that we assume today that the source is a point. So when we are nearer to the source than the possibility to assume it is a point, we have to take care about this. And we will see that it is maybe the most important kinematic parameter. And we left it out of the door. So please, accommodate one place more. Okay, that's the worst. But I will leave it for Monday. But it's very simple, actually.
Not the worst. Great is worse.
Okay, you're right. So let's close today with the best. That's beautiful.
Exactly. Yes.
It's beautiful. No, it's not. But remember, according to the specific target that you have, if you're dealing with focal mechanism, you will use just this. And this is easy. We have used it. Sines and cosines. Maybe you're going to use the near field term, but once you give a look just to that, it's again sines and cosines. What is the real problem is that these expressions here are for homogeneous infinite elastic medium. That's been worse. So just to sum up, please, if you want, of course, but it's my suggestion, if you can, in the weekend, look at the beautiful video. It's taking 8 minutes, it's very nice. Give a, how to say, a read to this nice sort of manual, and if you want, just give again a look to that piece of paper. So what we're going to do on Monday will be to discuss the Haskell model. That will be the necessary step to define magnitude, the modern magnitude. But before, we have to understand the original definition of magnitude by Charles Richter. And to do that, we would like to know what is a Wood Anderson instrument, because he was using those words. So he tied the definition of magnitude, that is very simple, to a specific instrument. And he knew about this. That's why he was not saying, wow, universal magnitude. Actually, he was one of those suggesting to use for his magnitude the nickname local magnitude, because he was aware that he was using California earthquakes with specific tables and a specific instrument. That's why Richter's magnitude nowadays is called local magnitude. Okay, that's the prequel. So, have a nice day. By the way, the two lectures that we have been developing on Monday, Wednesday, they are online. What is missing is the Friday's lecture. That was terrible.
Thank you.
You're very welcome. Goodbye. Have a nice weekend.
Bye. Bye.
And combine the object in one mode, it would be PM3 and N1 PL1 plus N2 PL2. But we have to choose N1 and N2 in such a way that we should have to reduce the effect of the ion spread effects on the
Signal, on the frequency.
no, on the global positioning system.
On GPS. Yeah, the signal coming from GPS.
So, like in the expression that she gave, she chose like I don't know exactly what she chose like.
Yes, good.
F1 is square, PL1 minus FT square, PL2.
No, she puts L1 and L2.
That's indeed the
Okay,
observed
L1.
for first
Yeah.
frequency and observed for second frequency.
Okay,
So this is,
yeah, okay. This represents L1, this represents L2.
yeah. So
Okay.
we have to
so
solve this. Just
She's asking for what is N1 and N2.
no.
Okay, continue.
So N1 and N2 is now N1 is F1 square by F1 square minus FT square, and N2 is minus FT square by F1 square by minus FT
Okay,
square.
what is the class here? What?
So it's minus F1 FT square by F1 square minus FT square.
N2, N2. N2 will be minus this
Minus
one.
this
Okay,
one.
okay.
So now let's solve this. Whether it fits by minus square, you know that fit or not. That's our
Oh, okay, we want to try to prove.
yeah. Okay.
Oh,
See. Is that right?
I see that. N of F1.
Delta P, I think something we should. T square. T plus C.
She says either we use the face one, the code is the same. But I think we should use face.
Yeah. F2. If you solve this, F1 minus FT square D. So D plus C, delta T satellite, delta T distributes isolated. And everything here is. And F1 square times this.
Okay, just continue.
So this is indeed this. Minus C by F1 square times total electron concentration minus F3 square minus C by F3 square times total electron concentration. So it's cancel. And minus plus it's 0.
Okay, so it doesn't affect it.
So frequency 0. Everything is 0. So there is no
This is multiplied this. Okay, so it doesn't affect it. Okay, just need to sit and get it.
but I don't know whether it's
No,
This is
it's
the
just
point
for us
that's
to make
here.
an attempt. Once you do at some point.
this is it. Excuse me, sir. Yes. Do we need to remember the equations in exam or?
Some of them, not all V, as I told you, not all V algebraic flow,
Okay.
but the most important ones,
Final.
yes.
Okay.
Yeah, the final ones, like MPQ, convolved G, and PQ. That one is a must, okay, but not all of them, definitely. Just the logic, yes, the logic.
If you switch over
Yes.
Oh,
Oh, I thought yes.